Very good morning to you all. I welcome you all to this stochastic processing subject. So, according to the stochastic processing subject, we discussed in the previous classes, random variables, one-dimensional, two-dimensional, and n-dimensional, properties of probability distribution, probability density function, cumulative distribution function, and evaluation of statistical parameters for random variables, and some of the important random variables and its probability density function and the cumulative distribution function, its use in communication engineering. And also we discussed in the previous class, very previous class, we introduced the concept of random process. I have considered it with an example. For the sake of clarity, I want to repeat the same. Random variable is mapping of the sample space onto the real axis is a random variable. All the ways, generally people think that random variable is a variable. No, it's not a variable. It's a function. Mapping of points in the sample space onto the real axis. Is a random variable. A random process is ensemble of random variables. Exact meaning is collection of different random variables. I will show you a typical example here, which is provided in this book. So this example, if I am considering at 0th instance of time, xn plus 2 of t, xn plus 1 of t, xn of t, x of n minus 1 of t. This I can consider it as a random variable. This I consider it as a random variable. And whatever the statistical calculation, mean, variance, correlation, kurtosis, everything we discussed in the previous chapter will be calculated for a random variable. Those statistical parameters, those means are generally called as ensemble averages. That are called ensemble averages. It is calculated for a random variable. Random variable means this is one experiment, a typical experiment done at first level or first case, second case, third case, and fourth case. It's a random process. Consists of ensemble of random variables. And if you take average of the values or the mean, kurtosis, or whatever the statistical parameters calculated for these random variables, we call it as an ensemble average. And one more new parameter will be introduced in the random process is time average. If I calculate the average along the time axis, which is called time average. So the parameter, this is ensemble average, and the parameter will be time average. Two important points. Ensemble average, till now we discussed the averages are mean, correlation, kurtosis, all the values are, we call them as expectation of x or expectation of x square. Those are ensemble averages. And we'll define in today's class what is time average. And see here, x of t1 comma s is generally represented as x of t1, which is a random variable. because the t1 we are mentioning it as a constant when the moment time is constant. See, random variable is a function of sample space. Random variable is function of sample space S. Random process is function of both time and S, both the time and sample space. So that is x of t comma s is a random process. The moment t becomes constant, say t1, then that is x of t1 comma s, which here represented as x of t1, which is a random variable. It is a random variable. Same thing. If time is constant 0, and this is called random variable. So ensemble average, time average, ensemble average and time average. And we mentioned in the previous class that just a classification is there in this book. Just to go through the continuous random process, a discrete random process, for different classifications are there. Just you can refer that. Now, the next important concept, which is very important, is stationarity and independence. Stationarity and independence. Next classification is there. One more classification is there, which is called ergodic random process or a non-ergodic random process. Random process characterization, ergodic random process, non-ergodic random process, stationary random process, non-stationary random process, random process classification. And mostly in the design of wireless communication system, in the question he will give whether it is a stationary or non-stationary, whether it is a ergodic or non-ergodic. Generally it will be mentioned in the question. That is a discrete time channel adding a wide sense stationary random process of noise with variance 1. This may be a question, looks like. A discrete time channel adding noise. What is the characteristics of the noise? Noise is a wide sense stationary Gaussian random process. Wide sense stationary Gaussian random process. So, mean, stationarity and independence, these two parameters are very much required while evaluating the problems related to wireless communication system. So, I will provide a good example here, or a good definition provided here. Just I will read, see that. That is, a random process is said to be stationary if all its statistical parameters do not change with the time. Then we call that as a stationary random process. What are the statistical parameters? What is the statistical properties? Mean, variance, joint movements, movements about mean, movements about origin. All these are statistical parameters, which we are calling it as ensemble averages. Those are ensemble averages. And we will say a random process is said to be stationary if all its statistical parameters do not change with the time. Very interesting statement. Once again, I'm reiterating the sentence. Broadly speaking, the random process is said to be stationary if all its statistical properties do not change with the time. See, all statistical properties will have E of x, E of x square, E of x minus mu, E of x minus mu whole square. Each formula, if you see perfectly the formula, that minus infinity to plus infinity, whatever there in the inner brackets of expectation, copied down here to the integration, multiplying it with fx of x, that is probability density function. If it is a first order, we'll say fx of x dx. If it is a second order joint density function, fxy of xy dx dy. So when we say the statistical properties will not change with the time, if its density function does not change with the time, automatically all the statistical properties will not change with the time, because all statistical properties, the formula is expectation multiplied by the probability density function. If the probability density function does not change with the time, whether it is a first order, second order, or nth order, first order, second order, or nth order, whichever it is. So broadly speaking, once again I am reiterating the formula. Stationarity, broadly we are saying stationarity, that all the statistical parameters does not change with the time, implies the density function will not change with the shift in time, not change with shift in time, not change with shift in time. So that is the wonderful definition given by this book or any for stationarity in broad sense. In broad sense. Now we'll see. Otherwise, if it is not, if it is depends with the time, then we call it as a non-stationary random process. The statistical parameters are changing with reference to time, then I can say that is a non-stationary random process. Typical example I will mention here now. Now, I have calculated the mean at this instance of time at say t is equal to 0. Now, I have calculated the mean average value, ensemble average expectation of x at t1. If these two values are same, we can say it's a stationary random process. Example I'm considering here. Example I'm considering. If for a random process, I'm calculating the average value at t is equal to 0. I'm calculating the average value at t is equal to t1. If these two values are same, we can say it is a stationary random process. So what's the definition of stationarity in broad sense? Stationarity in broad sense. And see here, x of t is a random process, x1 is a random variable. So yeah, I'm considering first order distribution and density function. So fx x1 comma t1 is equal to, that is capital Fx means it's a cumulative distribution function. Probability x of t1 less than or equal to x1. Property is same. So same thing will be applicable to distribution density function. That is first order. Now, second order, for two random variables, x1 is equal to x of t1, x2 is equal to x of t2. Second order joint density function, that is fx of x1 comma x2, t1 comma t2, that is probability x of t1 less than or equal to x1, x of t2 less than or equal to x2. See here, this is the first order distribution function. First order distribution function. This is second order distribution function, x1, x2, and so on. Now, nth order distribution function, fx of x1 to xn, t1 to tn, probability that x of t1 less than or equal to x1, and so on up to x of tn less than or equal to xn. Same I have provided in my formulas page very neatly. See here. x1 is equal to x of t1 is a random variable will denoted by its distribution function is denoted as capital Fx x1. Sorry, here x1 is missed. x1 comma t1. So fx1 of x1 t1 is equal to probability that x of t1 less than or equal to x1, It is a first order distribution function of the random process x of t. Similarly, if it is a second order x1, x2, then joint density function and joint distribution function will be defined. Similarly, for nth dimensional random variable, xi is equal to x of ti. I is varying from 1, 2, 3, and so on up to n. So fx of x1 to xn, t1 to tn, just now we have seen. Similarly, the properties of density and distribution function will not change. Will not change. That is, one-dimensional PDF is equal to derivation of one-dimensional CDF. Joint density function is equal to double differentiation dou square dou x1 dou x2 of joint density function. In the previous examples, we have considered x and y. Here, x1, x2, and so on. Similarly, nth order density function. Similarly, nth order density function. So, we introduced here one of the important concept, stationarity and one-dimensional random variable, two-dimensional random variable, n-dimensional random variable, drawn from a single random process. Drawn from a single random process. Now, next one is statistical independence. Statistical independence. It is if two random processes x of t and y of t. Now see here, x of t is one random process, y of t is another random process. If these two are statistically independent, that is fxy of x1 to xn, y1 to ym, t1 to tn, t1 dash, t2 dash up to tm dash is equal to individual density functions. That is density, n-dimensional density function of x multiplied by m-dimensional density function of y. This is we have seen in the previous classes that joint density function, if it is a statistically independent, fxy of xy is equal to fx of x multiplied by fy of y. Same thing is extended here. Same thing is provided again in the book, statistical independence. Statistical independence. Now we will see the detailed discussion of stationarity. Detailed discussion of stationarity. So first order stationary process. That is, a random process is called stationary to order 1. See, the first definition we have given that broadly speaking, stationarity means if it's all statistical properties does not change with the time. Now, stationary to order 1, a random process, say x of t, is called stationary to order 1 if its first order density function does not change with a shift in time, with a change in time. Does not change with shift in time. So that's definition is given here. F x of x1 colon t1 is equal to f x of x1 t1 plus delta, or we can define it as a t1 plus delta. Delta is some real number. So if the density function, first order density function, does not change with the time, we call it is a stationary to order 1. Now it's only given density function. Now we'll see how the mean and other values will change. That is, expectation of x of t is equal to x bar is equal to constant. How? We'll see it here. Expectation of x1 is equal to expectation of x of t1 is equal to minus infinity to plus infinity x1 fx of x1 comma t1 dx1. Now e of x2 is equal to x of t2, that is minus infinity to plus infinity x1 fx of x1 t2 dx2. if I substitute T2 is equal to T1 plus delta, because these two are does not change with the time. Expectation of x1 is equal to expectation of x2. If it shift in time, if it is shift in time, that value, the dependence, that is density function, does not change with the time, then mean is also constant. This first order stationary random process. Same thing is given here. Fx of x1 comma t1 is equal to fx of x1 comma t1 plus delta, that is constant. X of t1 plus delta is equal to x of t1. Even shift in time, the mean value will not change. The mean value will not change. Why? Because its density function is independent of time. Its density function is independent of time, or it does not depends on shift in time. Now, second order process is generally we call second order stationary random process is generally called as wide sense stationary random process. Second order random process, if it is stationary, then we call that as a wide sense stationary random process. Nth order random process, nth order random process, if it is stationary, then we call it as a strict sense stationary. So WSS, wide sense stationary, it's a second order random process. Strict sense stationary, SSS 3S, it is a strict sense stationary random process. Now we'll see, now you see here, now you see here, just I'm moving to this point. Second order wide sense stationary WSS process, Fx x1 x2 t1 t2 t1 plus delta t2 plus delta t1 plus delta t2 plus delta. I will go to the book preferably, right? So same thing is given here. x1 x2 t1 t2 is equal to x1 comma x2 t1 plus delta plus t2 plus delta. That is, joint density function does not change with the time. Joint density function does not change with the time. Now we know this is called autocorrelation. We'll define this as autocorrelation. Rxx t1 comma t2 t1 expectation of, see, we have seen the correlation function in the random variables. In the random variables, expectation of xy is called correlation. Expectation of xy is correlation. Here both are x of t1 and x of t2. We call it as a x1 random process, x2 random process. Sorry, x1 random variable, x2 random variable. Both drawn from x random process. Both drawn from x random process. So Rxx is equal to Rxx of t1 comma t2 is equal to expectation of x of t1 into x of t2. And sometimes, generally, preferably, always remember that difference between these two inner indices will be the value here. Generally, t1 t1 plus delta minus t1, the inner index of x of t1 plus delta is t1 plus delta. Inner index of x of t1 is t1. T1 plus tau minus t1 gives to t1, and t1 nullifies, tau will be remain. So tau, generally the brackets, inner brackets of autocorrelation function is generally the difference, the time indices of expectation value. Difference in time indexes of expectation value. So same thing is provided in the formula also. So Rxx of t1 comma t1 plus tau is equal to expectation of x of t1 into x of t1 plus tau. The difference between these two time indices is tau. That is, mean and autocorrelation are constant in wide sense stationary random process. Mean and autocorrelation. Mean and autocorrelation does not change with time. Mean and autocorrelation function does not change with time. Expectation of x of t is equal to x bar constant. Similarly, it is depends on only tau, not on t1 and other values. It depends only on tau, not on t1 values. So, stationary random process of order 1 we have seen. Stationary random process of order 2, which is also called as wide sense stationary random process, which is also called as wide sense stationary random process. Now, continuation nth order strict sense stationary random process. That is, its nth order density function does not change with time. Does not change with time. So we'll call it as nth order stationary random process. So mostly I will stop at this point because we have defined so many parameters today. We have defined so many parameters till now.